So far we have completed 6 number of videos. Up to this 6 number of videos, we have seen the analysis in full. By the end of this 6 videos, we have already arrived the uniformly distributed load over the slabs, uniformly distributed load over the beams, the bending moment in beams, the axial load on columns, and the column moments. So far, we have seen these things. Next chapter is to design the individual section members, structural members. That is, arriving the size of the structural member and what is the reinforcement to be provided. Those things we are required to do this in next. The first video, which is the seventh video, here I am going to design the slabs at the first. The slab design is a simple thing. This can be done with the use of IS 456 2000 and design aids to IS 456 2000. With this, I have explained very clearly and easily, which is more acceptable by most of the people in India. So please follow these things carefully and you can have a better idea how to design the slabs. The persons who did not follow those videos so far, please follow my videos. Please scroll my video list and see my all videos from video number 1 to 6, and now you will have a better idea to continue further. Please follow the video. Please like and share and subscribe. This is the beam layout and may be called as column layout. These are the columns and these are the beams. These things we have already discussed in previous videos, and now I have given the names to each panel. Panel means the slab in between the beams is called the panel. This panel I have given the name as 1, this 2, 3, 4. Likewise, I have given the names to each panel. This is staircase, that's why I did not give any names to this. These are cantilever slabs, which we will see this later. Okay, these things, we need not have to design the slab for all the panels. We can find out which are the different and vulnerous panels for which we should design. If we take this panel number 2, if it is taken as this is a long span, this comes as under one way reinforcement. This length by width is more than 2, so this we are going to design this as a one way reinforced slab. And 4 and 3 are the same, so 4 we can design. And the 7 is the 3.35 meter by 5.1 meter. This span is different. So 1, 2, 3 are the different spans which have lesser width and a long length. This panel number 8 and 9 are the same. For this, the 8 and 9 are the two-way reinforcement with approximately equal sides in both sides. So we in vulnerable spans are panels are 2, 4, 7, 8. If required, we can take this 5 also, 5 or 6 also. Selected the panels named as 2, 6, 5, 8, 7 and 8. The span lengths, short span length and long span length I have given here. The critical span, I think the critical span can be the panel number 7 or panel number 8. The loading, the partition wall is there in panel number 5 and panel number 8. So for that I have added the weight of that partition wall, that I have worked out as 1.49 kilonewton per m square. See here also the higher length is higher, so this comes out as 2.9 kilonewton per m square. This total comes as 10.1. This total comes as 8.75. In all other places 7.25 kilonewton per m square, which we have already worked out, which we saw in that video number 1 or 2. So based on this, we are going to design the slabs. For the designing these 5 slabs itself is enough for giving the drawing to the entire building. We shall move to that next chapter of finding the depth of the slab, which is safe against deflection. Uh, please note that if a slab is given a proper reinforcement, then the slab will not fail due to bending. But the deflection will be there, which will cause sound in the deflection, and the people walking over the slab will not feel better. So, we should decide the depth of slab. IS code given certain uh, procedures to find it out. Okay, now we are going to the procedure of finding the depth of slab. Now the short span we are going to that is we are going to find that slab depth for the slab named 7, number 7. For that, the short span is Lx is this 3.35, Ly is this 5.1. Uh, working load is 7.25 kilonewton. Concrete grade is M20. Steel grade is Fe 500. Slab is rested over beams which are continuous. This slab is rested over beams and the slab is continuous. Okay. The class 23 to 1 of IS 456 describes the procedure to find the depth of slab. Yes, this comes under control of deflection. For that, a continuous structural member in flexure should have the basic value of span to effective depth ratio. Span to effective depth ratio up to a span of 10 meter for a continuous beam or continuous slab is 26. This 26 can be multiplied by a modification factor. The value of this value of A can be modified with a modification factor obtained in figure 4. What is figure 4? This is figure 4 where the modification factor has been given. The percentage of tensile reinforcement is given here. Our tensile reinforcement is generally remain below zero point 0.2. This is 0, this is 0 0.4, 0 0.5, 1 point, 0 0.8, 1.2 and etc. Now, generally for a slab, the reinforcement generally remain about 0.3 or 0.4, something like that. If it is 0.3 is taken, this value Fs equal to Fs means the stress in the working stress in the main reinforcement is 240 Newton per mm square. This we may approximately will decide these things. For this, the modification factor it has been set as 1.6. But instead of taking 1.6, if we take the modification factor as 1.6, that can be multiplied with this 26 for the continuous. If it is multiplied with that, this will give you a very huge figure. So we shall take this modification factor as 1.2. That will give a value 26 into here notice span to effective depth ratio is 26 into modification factor is taken as 1.2. So span to effective depth is 31.5 that we have decided. Now effective depth means that is 3.35 is the short span into 1000 is for converting into mm divided by 31.5. This ratio this comes as 1 point, so it is 106.3 mm is the effective depth. Add the cover, this comes as 126.3, take it as 127 mm, which is approximately 5 inches. For the slab number 7 we have arrived. Similarly, slab number 4, similarly, if we work out this also comes as 127 mm, just 5-inch thickness. Other slabs are with similar spans, so above depth is okay for all other panels also. Slab can be with a minimum depth of 11.5 centimeter, that is 4.55 inches in practical condition. In general, um, the viewers please understand that any slab in India is generally laid for a thickness of 4.5 inches minimum. If it is laid less than 4.5 inches, the deflection we shall feel that in practice we will feel the deflection, and also due to the wear and tear or the creep, the slab will sag a lot, and the people residing above or below will feel some way disturbed. So do not provide any slab less than the thickness of 4.5 inches. Now we are going to see what is the moment in each slab, that we are going to calculate from the tables available in IS 456. IS 456 describes has given a table which can be used to find out the moment in the slab. So these are the first 6 or 7 lines or the data we are already having with us. The name of the slab is number 7. LX means short span 3.35, LY means long span 5.1. The working stress, that is working load or service load, is 7.25. This has to be multiplied by 1.5 to find the factor design load. This is 10.875 kilonewton per inch square. That is load on the slab. Concrete is M20, F500. Fe500 is the concrete grade we are going to use. This slab number 7 has been supported is continuous on 3 sides, and the one short edge is at the end. So this is called 3 edges continuous and one edge discontinuous. This is called in this way. So now this is Ly by Lx means 5.1 by 3.3. Its value is 1.52. So using this table, we are going to find the moment in that slab. This is IS 456. This is the table number 26. Bending moment coefficient for rectangular panels is supported on 4 sides with provision for torsion reinforcement at the corner. Okay. This is item number 2 is the one short edge is discontinuous. This is the applicable category for the slab we have selected. So in this 1.2, these are the Lx by Ly value is 1.52. This we can take it as 1.5. In this category we are coming, the seal number 2 category we are coming. This value, there is negative moment at the continuous for the value of 1.5 Ly by Lx. The serial number 2, 1 edge discontinuous. This is the category where we should take the value. This is for short span. This is for long span. Okay. That I have brought here. 0.57, 0.04, this one. So what is the maximum moment in this? 0.57 into W Lx square. Here this here. Alpha means the modification, the coefficient of moment coefficient into WL square. This is the value for negative bending moment. This is the positive bending moment for in the x direction, that is in the short span direction. This is the negative bending moment in long span direction. This is positive bending moment in long span direction. So what is the maximum moment? In the x direction means the long short span. Short span between these two, comparing these two, this 6.95 is the maximum moment, and this 4.52 is the maximum moment in long span. These moments are in kilonewton meter. Now we are going to find the main reinforcement required to be provided. in the slab. This is design of floor slab, main reinforcement calculation. These are the data we are already having in it. The maximum moment in the short span, we have already found it, which is that is 6.95 kilonewton meter. This is the maximum moment in the short span. 4.52 is the maximum moment in long span that we are going to take for the design of this thing. Okay, this total depth of slab is 130 mm, effective depth is 110 mm. Now we are going to use the chart number 16 in design aids to IS 456. This design aids to IS 456 is also called as SP16. If anybody wants to download this is easily available in net. You can search in website searching that is design aids to IS 456, or you can search as SP16 also. This is easy, these free downloads only you can find it. That we are going to see. So now what is the data we are already having? The moment is already we are having here. So based on that moment we are going to calculate. We are going to use the chart number 16. This is the chart number 16 in the book called Design Aids to IS 456. This can also be called as flexure member, singly reinforced section, moment of resistance in kilonewton meter width of the slab. We are going to calculate the moment of resistance or the bending moment maximum bending moment of the slab which can be resisted by that slab is called the moment of resistance in that slab. The data we are having FY 500 is the steel, FCK it is concrete grade is M20. This is a chart between reinforcement percentage. In the vertical column, this is in the y-axis, it is the depth in centimeter. That is, we are going to we are providing a slab for 11 centimeter. That is 110 mm, 1100 mm. Okay. For the kilonewton, a moment is 6.95, means this is 7 kilonewton meter. So for corresponding to 7 kilonewton meter, there is a graph. These are graphs which have been this is for 7 kilonewton corresponding to 7 kilonewton meter. This is the graph prescribed in the code book. Here we are going to use this centimeter length. Depth of the slab is 11 centimeter. So it is corresponding. This coordinate comes up. This is tracking down. This is 1.1, 1.2, 1.4. This is 1. We have taken this 0.14. We have taken here. This 0.14 is PT means that is AS. PT percentage of steel into 100 for the percentage divided by 1000. 1 meter into the 1 meter means 1000 mm into 110 mm depth is equal to this much. On equating this, corresponding to percentage steel, the square mm is 154 square mm. On calculation of this, 154 square mm of steel is required for 1 meter length of slab. For calculating this, area of cross section of 8 mm diameter is 50.24. This you can calculate and find it out. If the number of rods required for this is 154 is the total square mm of rods required divided by this 150 something. Sorry, 550 plus 24, totally 3.03 rods of 8 mm diameter is required for 1 meter width of the slab. Space in corresponding slab is 1000 mm divided by this number equal to 325.73 mm. But the 8 mm rod is used. 325 one rod may the spacing of rod is 325.73 mm, this spacing. But uh, the same code prescribes that the maximum spacing between two rods can be the depth of slab into 3 is the maximum spacing between two rods. But in practice, this condition is not good, so we are reducing it to 2.5 only. So on multiply allowing the allowed spacing is 111 is the effective depth into 2.5 is the coefficient of multiplication. The total comes as 275 mm is the maximum spacing of two rods in the designer in the for providing in the slab. So the same maybe this 275 is less than the design value of 325 mm. So we are going to provide this 275 mm with the spacing between two main rods, that is 8 mm main rods. So the result is 8 mm rods at 275 mm center to center is the result. But do not provide, this is not the final thing. I have given this in execution and practical adoption will be considered. Please watch till the end and the next video. The slab, because the slabs generally have little seepage during the utility. So this seepage or the dampness cast may cause corrosion in the steel. So atom rods may get corroded shortly. So generally we are using 10 mm rods in this phases later, that we shall think do in the last of it. For the same design for the long span, the same moment and the using the same table, we are arriving that this is spacing as per the design is 380.25 mm as per the design, and the maximum spacing allowed is 275. So we are the result is 8 mm rods at 275 mm center to center in long span also. The roof slab. Here, during actual construction, the concrete strength will not be same in all the places in the floor slab or roof slab because of the load by the walking ladders and the impact of concreting. So, a provision has to be given additionally to nullify the effect due to this improper packing or collection of coarse aggregate in some place and the collection of fine aggregate in some other place, which causes less strength in the concrete in some of the selected points. So you suggested that the green lines are the 10 mm rods and the blue lines are 8 mm rods. I have suggested that 10 mm rod at a spacing of 175 mm, 8 mm rod in the long span at a spacing of 175 mm. Both are at 175 mm spacing for the span of 3.35 meter short span and 5.15 meter in long span. The same can be adopted in all other slabs because all other slabs are also crucial, but it is not as vulnerable as this span number 7. So the same rods will be used in all the spans. This is the actual drawing. This crank, the rods which are going straight and bend, these rods are called crank rods. The center point in any span, the middle of the span, the rods should be kept in flush with the bottom, and the support point, the rods should be in flush with the top layer. Another rod will be a straight rod which is placed in flush with the bottom. This is the usual what are usually adopted. In addition to these rods, the hanger rods and chair rods and corner reinforcement rods are to be provided. These things we shall see in some other video at the end after completing this design lecture.